We live on a planet, a beautiful blue sphere teeming with life, hurtling through the vastness of space. For centuries we have understood this home of ours to be in constant motion, and not just orbiting the sun, completing a grand journey every year, but also spinning on its own axis. This spin, we are taught, gives us our days and nights. It's a fundamental concept, a cornerstone of how we perceive our place in the cosmos. Imagine Earth as a giant celestial dancer, endlessly pirouetting in the grand ballet of the universe. This motion seems as real as the sunrise. This idea of a rotating Earth wasn't just a wild guess. It came from careful observation and brilliant deduction. Early astronomers watched the stars parade across the night sky. They charted the sun's daily arc. These celestial movements strongly suggested that our planet itself was turning. Later, scientists discovered phenomena like the Coriolis effect, which influences weather patterns and ocean currents. This effect is elegantly explained by a spinning Earth. The evidence piled up, painting a picture of a dynamic, rotating world. It became a truth woven into the fabric of our scientific understanding, a daily dance we all participate in, knowingly or not. Perhaps one of the most compelling visual demonstrations of Earth's rotation is the Foucault pendulum. First conceived by Léon Foucault in 1851, this ingenious device consists of a heavy bob suspended by a long wire from a fixed point. Once set in motion, the pendulum swings back and forth, but here's the magic over time. The plane of its swing appears to rotate. In the northern hemisphere, it seems to turn clockwise, in the southern counterclockwise. This apparent rotation is hailed as direct proof that the Earth is indeed turning beneath the pendulum. It's a silent, graceful testament to our planet's spin. But what if this familiar story, this cosmic ballet, has a hidden layer? What if the Foucault pendulum's dance is influenced by something more subtle, something we've overlooked? Science is a journey of constant questioning. Even the most established ideas are open to scrutiny if new evidence emerges. Could the pendulum's perceived rotation be telling us a different story about Earth's motion? Or perhaps about the very nature of motion itself? It's a thought that invites us to look closer, to listen more carefully to the whispers of the cosmos, and to reconsider what we think we know. Let's delve deeper into the mystery of the Foucault pendulum. How does it supposedly reveal Earth's spin? Imagine you are looking down at the North Pole from high above. The Earth is turning counterclockwise beneath you. Now picture a pendulum swinging at the pole. Its swing direction is fixed relative to the distant stars because no forces are acting to change it. However, because the Earth is rotating underneath it, an observer on Earth would see the pendulum's swing plane rotate clockwise, completing a full circle in about 24 hours. This is the classic explanation. The beauty of this explanation lies in its elegant simplicity and predictive power. The apparent rotation rate of the pendulum's swing plane is not the same everywhere on Earth. At the poles, it's fastest, making a full circle in one sidereal day. At the equator, the pendulum's plane doesn't rotate at all relative to the ground. At any latitude in between, the rate of rotation varies, specifically with the sign of the latitude. This precise mathematical relationship has been confirmed by countless experiments around the world. It seems to lock down the idea that the pendulum is a faithful indicator of Earth's rotation, a mechanical witness to our planet's ceaseless turning. For over a century and a half, the Foucault pendulum has graced museums and universities worldwide. It stands as a powerful educational tool, offering a tangible connection to the abstract concept of a spinning planet. Millions have watched its slow, majestic drift, accepting it as visible proof of the Earth's daily rotation. It's more than just an experiment. It's a symbol of scientific enlightenment, a testament to human ingenuity in uncovering the workings of the cosmos. The pendulum's whisper seems to be a clear and unambiguous message about our planet's motion, a message that has resonated through generations of scientific thought. But science is a relentless detective. It never truly rests its case. What if the pendulum's message has been misinterpreted? What if the echoes of rotation are in fact something else entirely? Sometimes the most profound discoveries are made when we question the interpretations of even the most cherished evidence. The universe is full of surprises. It often communicates in subtle ways. Perhaps the Foucault pendulum's whisper is not as straightforward as we have believed. Could there be another layer to its story, a nuance that changes everything we thought we understood about its graceful, predictable dance? Now let's consider a fascinating and provocative observation. Imagine setting up not one but two Foucault pendulums. They are identical in every way that traditionally matters. Same mass, same length of wire, swinging in the same location, side by side. There's just one crucial difference: the material of the pendulum bob. One bob is made of metal, a good conductor of electricity and potentially susceptible to magnetic fields. The other bob is made of plastic, an insulator, non-conductive and non-magnetic. This simple difference sets the stage for a truly unexpected outcome, one that challenges conventional wisdom. According to new experimental claims, when these two pendulums are set in motion, something remarkable happens. The metallic pendulum behaves as expected, its swing plane slowly, steadily drifting, seemingly tracing the Earth's rotation, just as Foucault himself observed. It dances the familiar dance. But the plastic pendulum, its non-metallic counterpart, reportedly tells a different story. It swings back and forth, dutifully marking time, but its plane of oscillation shows no rotational drift. It just keeps swinging in its initial direction, oblivious to the supposed rotation occurring beneath it. This is a startling divergence from the norm. If these observations are accurate and repeatable, they present a profound puzzle. The traditional theory of the Foucault pendulum attributes its drift solely to the Earth's rotation. The material of the bob should be irrelevant. Mass, length and latitude are the key factors. Yet here we have a situation where material properties seem to be the deciding factor. The metallic pendulum sees the rotation, or something that mimics it, while the plastic one does not. This suggests that the interaction causing the drift might not be purely inertial, as traditionally believed, but might involve electromagnetic properties or some other material-dependent interaction. This unexpected twist forces us to ask some fundamental questions. Why would a metallic bob drift while a plastic one under identical conditions remains steadfast? Is the drift of the metallic pendulum truly due to Earth's rotation, or is it responding to a different, unseen influence that only affects certain materials? This observation, if confirmed, doesn't just tweak our understanding of the Foucault pendulum. It potentially sends ripples through our understanding of Earth's motion and the forces at play. It's a scientific cliffhanger demanding a new explanation, a new way of seeing. The curious case of the differing pendulums, metal drifting, plastic static, opens the door to a radical new idea. What if the Earth isn't primarily defined by rotation in the way we've always thought? What if instead our planet is in a state of resonance? This is the core of a challenging hypothesis that the Earth resonates, and this resonance, not rotation, is what influences the metallic Foucault pendulum. It suggests that the motion we attribute to spin might be an illusion, or at least a misinterpretation of a more fundamental vibratory state. This is a bold claim, one that asks us to listen for a different kind of planetary music. So what exactly is resonance? Think of a guitar string, pluck it and it vibrates at a specific frequency, its natural resonant frequency. Push a child on a swing. If you push at just the right rhythm, its resonant frequency, the swing goes higher and higher with minimal effort. Resonance occurs when an object or system is subjected to an external force that matches its own natural frequency of vibration, causing it to oscillate with a large amplitude. It's a fundamental principle in physics, seen everywhere from musical instruments to the tuning of a radio. Could our entire planet be part of such a resonant system? According to this alternative theory, the Earth's resonance creates a kind of pervasive field, an energetic environment. It's this field, the hypothesis suggests, that interacts with the Foucault pendulum. The pendulum, then, is not a passive observer of Earth's rotation under an unchanging sky. Instead, it becomes an active participant, its behavior dictated by its ability to tune into or interact with this planetary resonance. This shifts the focus from a simple mechanical effect of a spinning frame of reference to a more complex interaction between the pendulum's material and an encompassing resonant field generated by the Earth itself. This is a profound shift in perspective. To propose that Earth resonates rather than rotates in the context of explaining phenomena like the Foucault pendulum is to challenge a pillar of classical mechanics and observational astronomy. It requires us to imagine our world not as a spinning top, but perhaps as a colossal bell humming with specific frequencies. Such an idea naturally faces skepticism, yet science progresses by exploring even the most unconventional hypotheses, especially when confronted with anomalies that existing theories struggle to explain, like the differing behaviors of metallic and plastic pendulums. The tune Earth hums might be far more complex than we ever imagined. Section 5. The universe's hidden harmonies, frequencies of resonance. The proponents of the Earth resonance theory offer mathematical arguments to support their claims. They start by looking at the frequency traditionally associated with Earth's rotation. If Earth completes one rotation in approximately 86,400 seconds, or one sidereal day, its rotational frequency is about 1 divided by 86,400, which equals roughly 0.00001157 Hz, or 1.157 times 10 to the minus 5 Hz. Using the speed of light, approximately 2.99792 times 10 to the 8 meters per second, the wavelength corresponding to this frequency would be immense, approximately 2.59 times 10 to the 13 meters. The argument made is that this incredibly long wavelength doesn't seem to fit any known natural standing wave mode or wave structure for a planet of Earth's size. In contrast, the resonance theory proposes a set of entirely different fundamental frequencies for the Earth system. These are much higher. For example, 0.5 Hz, 2.0 Hz, and 9.0 Hz. The wavelengths corresponding to these frequencies are significantly shorter, and according to the theory, more in line with plausible physical structures or resonant cavities. For instance, a 0.5 Hz frequency corresponds to a wavelength of about 6.0 times 10 to the 8 meters, and a 9.0 Hz frequency to about 3.3 times 10 to the 7 meters. These are still vast, but orders of magnitude smaller than the wavelength derived from the daily rotation period. Furthermore, the theory delves into the relationships between these proposed resonant frequencies, highlighting what it calls D-frequency couplings. For example, the difference between 2.0 Hz and 0.5 Hz is delta 12 equals 1.5 Hz. The difference between 9.0 Hz and 0.5 Hz is delta 13 equals 8.5 Hz, and between 9.0 Hz and 2.0 Hz is delta 23 equals 7.0 Hz. These specific numerical relationships and their sums, for example, a coupling energy 12 Hz is mentioned, possibly related to sums or combinations of these frequencies or their differences, are presented as evidence of a harmonically interlinked system. Such harmonic relationships, it is argued, are characteristic of a system that is in phase and fundamentally in a state of stillness or dynamic equilibrium rather than continuous rotational motion. These calculations, while simplified here, form a core part of the argument for a resonant Earth. The numbers are interpreted to suggest that Earth's behavior, and by extension the behavior of phenomena like the Foucault pendulum, is governed by a complex interplay of these natural, resonant frequencies. Instead of a simple brute force rotation, this model paints a picture of Earth as a finely tuned instrument, vibrating with a symphony of specific harmonically related frequencies. The universe in this view is not just about motion, but about underlying harmonies and resonances that shape the structure and behavior of matter and energy. Section 6. The pendulum's secret, a resonant response. So how does this Earth resonance hypothesis explain the curious behavior of the metallic and plastic Foucault pendulums? If the Earth isn't rotating in the conventional sense, but is instead resonating, the pendulum's drift must arise from an interaction with this resonant field. The key, according to this theory, lies in the material properties of the pendulum bob. Different materials, it suggests, will respond differently to this pervasive planetary resonance. It's like having different types of antennas. Some are tuned to pick up certain signals, while others remain inert to those same signals. Metals, particularly conductive ones, are known to interact strongly with electromagnetic fields. The resonance theory posits that the Earth's resonant field has characteristics that specifically affect such materials. The metallic pendulum bob, being conductive, is susceptible to this field. It couples with the Earth's resonance. This coupling induces the observed drift in the pendulum's swing plane. The drift, therefore, isn't a direct observation of the ground turning underneath a fixed swing plane, but rather an active response of the metallic material to the resonant energy of the Earth system. The metal effectively feels the hum of the planet. Plastics, on the other hand, are typically non-conductive and non-magnetic. They are electrical insulators. According to the resonance theory, these material properties make the plastic pendulum bob largely immune or insensitive to the proposed Earth resonance field. It doesn't tune in to the planet's vibrational energy in the same way the metallic bob does. As a result, the plastic pendulum simply swings back and forth, its motion dictated primarily by gravity and its initial momentum, without exhibiting the anomalous drift. It remains deaf to the resonant song that makes the metallic pendulum dance. This interpretation fundamentally changes the role of the Foucault pendulum. Instead of being a passive indicator of an independent terrestrial motion, rotation, it becomes an active detector, its behavior contingent on its material composition and its ability to interact with a specific planetary field. The secret of the pendulum in this view is not about observing Earth's spin, but about revealing a material-dependent sensitivity to Earth's fundamental resonant state. It suggests that the very fabric of our planet might be alive with vibrations that only certain materials can perceive and respond to, a subtle dance between matter and planetary energy. Section 7. Shaking the foundations. Why new ideas face a cosmic headwind. The idea that Earth might resonate instead of rotate, or that its resonance governs phenomena like the Foucault pendulum's drift, is undeniably radical. It challenges concepts that have been foundational to physics and astronomy for centuries. Earth's rotation is not just an isolated fact, it's deeply embedded in our understanding of celestial mechanics, geodesy, meteorology, and even our measurements of time. To question it is to pull at a thread that could unravel a vast tapestry of interconnected scientific knowledge. This is why such new interpretations naturally encounter significant resistance from the established scientific community. The evidence supporting Earth's rotation, as traditionally understood, is extensive and comes from many independent lines of inquiry. Astronomical observations, such as the apparent daily motion of stars, the phases of the moon, and the behavior of other planets, are all elegantly explained by a rotating Earth within a heliocentric solar system. The Coriolis effect, responsible for the circulation of weather systems and ocean currents, is a direct consequence of motion on a rotating sphere. Space agencies launch satellites into orbits calculated precisely based on Earth's rotation. The sheer weight and coherence of this evidence create a very high bar for any alternative explanation. New theories, especially those that propose a fundamental shift in understanding, always face an uphill battle. This isn't necessarily a flaw in the scientific process, it's a strength. Skepticism is a crucial tool. It ensures that new ideas are rigorously tested, that evidence is carefully examined, and that we don't abandon well-established models without overwhelmingly compelling reasons. The history of science is filled with revolutionary ideas that were initially met with disbelief, only to eventually triumph. But it is also filled with countless hypotheses that, upon closer scrutiny, did not hold up. The burden of proof always lies with the new claim. For the Earth resonance theory to gain wider acceptance, it would need to do more than just explain the anomalous behavior of metallic versus plastic Foucault pendulums. It would need to provide a comprehensive framework that can also account for all the other phenomena currently attributed to Earth's rotation, from the day-night cycle to the trajectories of intercontinental ballistic missiles. It would require extraordinary evidence, repeatable experiments, and a theoretical structure that is at least as robust and predictive as the existing model. Until then, it remains an intriguing but highly challenging perspective on the motion of our home planet. Section 8, a resonating reality ripples through our understanding. If for the sake of exploration we consider the possibility that Earth is fundamentally a resonant system, the implications extend far beyond just the Foucault pendulum. The theory proposed by Professor Stylianos Touloumidis in Science, A System at a Dead End, suggests that many fundamental aspects of our physical reality might be products of such resonance. This includes the values of physical constants like Newton's gravitational constant, the Planck length, and even the Hubble parameter, which describes the expansion rate of the universe. These constants, usually considered fundamental and unchanging, could instead be manifestations of an underlying standing light structure and frequency coupling. This perspective recasts the universe not as a collection of particles moving according to forces, but as a vast interconnected resonant structure. The cosmic microwave background, the faint afterglow of the Big Bang, has a peak frequency around 160.2 gigahertz. Could this too be part of this grand cosmic symphony of resonances? Such ideas challenge the very bedrock of modern physics, which often relies on models of particles, fields, and cosmic expansion without, as the theory's proponents might argue, fully understanding the fundamental structures that give rise to these phenomena. A resonant Earth would be just one piece in a much larger, harmonically ordered cosmos. Interestingly, even within conventional physics, new findings sometimes highlight the peculiar ways materials interact with Earth's properties. For example, very recent experiments in early 2025 by physicists including Christopher Chyba have reportedly generated small amounts of electricity using a device made of manganese zinc ferrite, angled specifically with respect to Earth's magnetic field and rotational motion. While this is interpreted within the standard model of a rotating Earth, it underscores the principle that specific materials can indeed have unique interactions with planetary-scale fields and motions. This echoes the resonance theory's core claim about material-dependent effects in the pendulum experiment, albeit explained differently. A resonating Earth could open up entirely new avenues of inquiry. Could such resonances be harnessed as an energy source, far beyond the microvolts seen in preliminary experiments aiming to tap rotational energy? Could they influence geological processes, biological rhythms, or even consciousness in ways we are yet to discover? If Earth hums with specific frequencies, understanding this terrestrial song could provide insights into everything from earthquake prediction to the subtle environmental factors affecting life. The implications are vast, painting a picture of a far more interconnected and energetically vibrant planet than a simple spinning rock. Section 9. The quest continues, listening for Earth's true song. We stand at a fascinating juncture. The Foucault pendulum, long a symbol of Earth's rotation, now presents us with a curious puzzle when its material composition is varied. The observation that a metallic bob might drift while an identical plastic bob does not under the same conditions demands our attention. It whispers of complexities we may have overlooked. Is it an experimental artifact, a misunderstanding, or a genuine crack in our long-held understanding of how our planet moves and interacts with the objects upon its surface? This is the heart of the scientific mystery. The Earth resonance hypothesis offers a bold, alternative explanation. It paints a picture of our planet not as a silently spinning sphere, but as a vibrant, humming entity, alive with specific frequencies. In this view, the metallic pendulum dances because its material nature allows it to hear and respond to this planetary song, while the plastic pendulum remains oblivious. This theory emphasizes harmony, interconnectedness, and stillness at a fundamental level, contrasting with the continuous motion of rotation. It's a vision of Earth as part of a universal symphony of resonance, a concept detailed in works like Professor Touloumidis' critical examination of modern physics. Science, in its noblest form, is an unending quest for understanding. It thrives on questions, on challenges to the status quo, and on the rigorous testing of new ideas, no matter how unconventional they may seem. The skepticism that such a theory faces is a natural and necessary part of this process. Extraordinary claims require extraordinary evidence, and the path to validating or refuting such a paradigm shift is long and arduous. Yet it is through such bold intellectual journeys that our comprehension of the cosmos deepens, often in the most unexpected ways. Ultimately, whether our Earth predominantly spins or primarily resonates, or perhaps engages in an even more intricate dance involving both, the invitation from the universe remains the same. It beckons us to keep observing, keep experimenting, keep questioning. The true nature of our planet's motion and its place in the cosmos is a story still being written. Each new experiment, each challenging theory adds another note to this grand composition. Our task is to listen intently, with open minds and rigorous methods, as we strive to decipher Earth's true song, and in doing so understand a little more about our magnificent universe.